All right, welcome back, Physics 20 class. Thanks for all of your feedback from last episode. A lot of what I heard is it was blurry, you couldn't see it, my voice is very monotone. Um, really not a lot of positive. So hopefully this setup works a little bit better. It's a little more zoomed in. Hopefully it's not as blurry, but again, we're going to keep trying getting better every time. So let me know how this goes. All right, our next topic we're going to talk about is perpendicular vectors. So when we're talking about perpendicular vectors, this is what you're going to need to be able to do. You can read through that yourself. I'm not going to go through that. What I'm going to go through is all the notes below. So when vectors are added together, we call this the resultant vector. Alright, so in a vector addition diagram, it shows that each vector is drawn tail to tip in the appropriate position. So you may read online, if you're looking, some different strategies for finding. The one I like to use and the one that I find works the best is tail to tip. So the resultant vector is the actual distance from the tail of the first vector to the tip of the last vector. That there is how tail to tip works. Alright, so let's look at this example. A boy rides his bike to the park and we want to find his resultant displacement if he rides for 14 kilometers west, then turns around and goes 10 kilometers east. This goes back to how you did linear vectors in grade 10 science. So he first goes 14 kilometers west, then he turns around and comes back 10 kilometers east. So if we go from the tail of the first vector to the tip of the last vector, that's his resultant displacement. We represent that with displacement r. So dr is equal to, let's make forward positive, backwards negative, negative 14 kilometers plus 10 kilometers. Right? He gets negative 14, positive 10. The resultant is negative 4 kilometers. Or that also means he went 4 kilometers west. Alright, that's pretty easy. This here is also not incredibly difficult, but this relates more to what you did this week or last week in your lab. So if we find his displacement, if he rides 14 kilometers west and then heads 10 kilometers north. So we start the same way. He goes 14 kilometers west, but this time he changes his axis and heads 10 kilometers north. Our resultant vector we draw from the tail of the first vector to the tip of the last vector, and that there is going to be our displacement. Not only do we have our displacement, we're going to need to find his direction, the angle at which he heads. So looking at his displacement first, this is just Pythagorean's theorem. A squared plus b squared equals c squared. So we have d squared is equal to 10.0 kilometers squared plus 14 kilometers squared. Alright, we take the square root of both sides, and when we solve that, his displacement is 17.2 kilometers. Again, we're not done. We need to find the angle at which he heads, the direction in which he's headed. So, we can use what we learned last week, SOHCAHTOA. Now we know the distance of all three lines now. However, we're going to use the opposite and the adjacent because those are the ones that are given to us. In case we made any mistake in our calculations, we would still get the proper angle. So if we're using opposite over adjacent, that means we're using tangent. So the tangent of the angle is equal to the opposite, 10 kilometers west, over the adjacent, 14.0 kilometers. Sorry, 10 kilometers north, 14 kilometers west. Alright, so when we're solving for theta, we are going to use theta is equal to inverse tan of 10 kilometers north divided by 14 kilometers west, and theta is equal to 35.5 degrees north of west. So we follow it, that's why we put our directions in our equations. We follow it north of west. So when we put all of this together, our final answer is his displacement is equal to 17.2 kilometers at 35.5 degrees north of west. On the next page, example 2 is very similar to example 1, so I'm going to allow you to try that one on your own. I will also attach my teacher's notes to Canvas, so if you need to double check on how you did, please check the Canvas. So what you need to note is when vectors are being added together, are forces. You must also include a free body diagram. So whenever you're working with a force, we need to have a free body diagram. So let's look at this next example, example 3. Jack and Jill are both pulling on a 13.8 kilogram object. Jack is pulling with 105 newtons of force to the north, and Jill is pulling with 91.0 newtons to the west. We want to determine the resultant force on the object. So the first thing we're going to do is we're going to draw out our diagram of what's happening. So first of all, Jack is pulling on, let's draw it over here. Jack is pulling up or north with a force of 105 newtons. The force of Jack is equal to 105 newtons. Jill is pulling to the west, so the force of Jill is equal to 91.0 newtons. If we plug that in now to our diagram, we can use our free body diagram as Jack pulled at 105 newtons north, Jill pulled with 91 newtons west, and our resulting vector is going to be from the tail of the first to the tip of the last. That there is going to tell us our net force. So it's all the forces acting on the object. So we also need to determine at which direction. So F net is equal to all the forces acting on it, which in this case we are finding the hypotenuse. So again, we're going to use Pythagorean's theorem. So F net is equal to 105 newtons squared plus 91.0 newtons squared, and we're going to take the square root of the whole answer. When we plug that in, that gives us an answer of 139 newtons.